All right. So first example here, say we're considering this is a second order y double prime minus y equals 0. And some of these guys, these are the type, that at the beginning of the term when we defined what a differential equation was, some of you could solve by just staring down, right? Second order y double prime has to equal y, so you ask yourself, oh, what function do I have whose second derivative is equal to itself? Some of these ones is staring down variety of solving, but just to go through the some of the cases, what you could see with the characteristic equation. So some things to note about this one. Well, it's second order, obviously. It is linear in y. It's also homogeneous. Homogeneous. A lot of E's. Constant coefficients. And that constant coefficients one is where a lot of times this attack of assuming that y equals e to the rx comes in. Okay? So because of this, we seek a solution of the form y equals e to the rx. Yeah.
Can we also say that it's autonomous, not that it's a certain thing?
Oh yes, it is autonomous. Yeah, you could start listing out all the adjectives you know about things. It is autonomous. It's second order autonomous. Y double prime equals y. So y double prime is a function of y only, not of the independent variable. In this case, I guess you can think of it as x. Right? Yeah. So it's autonomous, homogeneous, second order, linear in y. So let's assume, or let y equals e to the rx, and we want to find the conditions under which, that is a solution. What conditions on R make a function of this type of solution? So with that assignment, we know what R and R's, y prime and all that is. Y double prime looks like what? Minus y, and that's just e to the rx, equals 0. This works so well with constant coefficients because that e to the rx never goes away. And I factor that out, or divide both sides by e to the rx, however you want to think about it, but we get r squared minus 1 equals 0, right? So what are the solutions to this? 1 and negative 1, right? Okay. So we would know that y equals e to the 1x would be a solution, as would be y equals e to the negative 1x. Those would be, they are linearly independent, you can check. Okay? But regardless, any linear combination of them will also be a solution. So take the r equals 1, it would be c1 e to the 1x plus c2 e to the negative 1x would be a solution. Yeah? And since y1 and y2, well, since they are linearly independent, e to the x and e to the negative x, what does theorem 4 state about this? Theorem 4 is this big one. If we have two linearly independent solutions to the homogeneous differential equation, then any solution y can be written as a linear combination of those other two. In other words, there are no other different solutions to that. Every solution will be a linear combination of these functions. Okay. All right. So for this example, I'm going to call this equation 1 there, just off to the side. a little bit of review, and I've forgotten about these two. I've heard about them and all that, of course, but the hyperbolic functions, they're not that bad. Yeah, hyperbolic cosine. And so hyperbolic cosine, and I guess I heard that people pronounce that as cosh or cosh. Spell it out. All right. So hyperbolic cosine is e to the x plus e to the negative x over 2. And hyperbolic sine h. Sinh. I don't know. Yeah, e to the x, very similar, but minus e to the negative x over 2. Okay.
Do they have similar properties as the original cosine and sine?
They do. Yeah, they do. So, for instance, cosine, the cosine function is an even function, so is hyperbolic cosine. Sine is an odd function, so is hyperbolic sine. And interesting, you know, derivative of sine, not hyperbolic, but derivative of sine is cosine, right? Turns out that the derivative of hyperbolic sine is hyperbolic cosine. So it does follow sort of parallel a lot of properties. But the trig functions, derivative of cosine is negative sine. That throws everything off. But turns out that the derivative of hyperbolic cosine is just hyperbolic sine. They still have some, say, follow their own sort of like trig properties as well. Not trig properties, but they have some identities similar to the trig identities. I think that's where they get their names. Okay.
Question.
Yeah.
What about, like, if it's e to the ix,
Mm-hmm.
wouldn't that just, and e plus e to the negative ix over 2, wouldn't that just be cosine?
Yeah. Yeah, you could, because e to the ix is cosine x plus I sine x. Yeah. So those are similar almost, yeah. But yeah, we might do, not today, but yeah, we could talk about what happens if we get complex roots to the characteristic equation. Yeah. All right. So, claim is that all these guys are solutions, but another claim is that we can write y of x up here of equation 1 as a linear combination of these hyperbolic functions. Okay. But the question is, are those actually different? All right, well, our function, you know, our linear combinations are the form something times e to the x plus something times e to the negative x. It's not a stretch to say, oh, that might be, I might be able to write it as cosine, hyperbolic sine and cosine.
Should you just do the Wronski test for that right now?
Oh, yeah, that's a good question. Are these linearly independent?
Or are they, I mean, are they any different than like y equals c1 e to the x
Right.
plus c2 e to the x? Because didn't they just say coefficient of?
Right. In other words, are these functions, are both of these functions linear combinations of e to the x and e to the negative x? I think, yeah. 1/2 e to the x plus 1/2 e to the negative x, that's hyperbolic cosine. But here's the sort of proof. I'd want to find constants d1 and d2 that make y equal to hyperbolic cosine x plus d2 hyperbolic sine, or I'm just going to call it sinh. All right. All right, so replacing the hyperbolic functions with their definitions, cosine e to the x plus e to the negative x over 2, and hyperbolic sine e to the x minus e to the negative x over 2. And then combining, imagine distributing the d1 over 2, yeah. I want to gather powers of e to the x, or factors of e to the x. It would be d1 over 2 e to the x, and plus d2 over 2 e to the x. All right. Plus, now I'm going to distribute, I'm going to have d1 over 2 e to the negative x plus, oh, sorry, that's going to be minus d2 over 2 e to the negative x. Okay. So factoring out e to the negative x from those terms, I'm just combining, the like terms e to the x. I have d1 over 2 plus d2 over 2 e to the x plus, factor out the e to the negative x, I have d1 over 2 minus d2 over 2 e to the negative x. Now that looks a lot like a linear combination of this form. Oops. Right there. Right there. Yeah? So some constant times e to the x plus some other constant e to the negative x. Okay. So yeah. So it is a linear combination of those two solutions. All right. Should we do this 120? We got 30 minutes. Let's do one more example, and then we're just talk about the exam. All right. So another homogeneous equation with constant coefficients. All right, let's look at the equation y, and this is third derivative, plus 3y double prime plus 2y prime equals 0. So all of a sudden this is a third order. Okay. So linear, constant coefficients, homogeneous. We're going to try y equals e to the rx. All right. So let's follow that assumption. And if that's the case, what's the third derivative going to look like? E to the rx, right? Plus 3, second derivative is just r squared e to the rx, plus 2, and y prime would be r e to the rx equals 0. One more step, if we factor out or equivalently divide both sides by e to the rx because it is always non-zero, this would be our characteristic equation, r cubed plus 3r squared plus 2r equals 0. Okay. Now, how do we solve this? Yeah, factor out r first of all. We're going to have r, and this is r squared plus 3r to the first plus 2. Oh, we already factored something like this. So we get r times R plus 2, R plus 1?
You have 3.
All right, so there are 3 solutions to this, yeah? Okay, so we get, what are they? 0, negative 2, negative 1, and this is 3 distinct roots. All right, so following the example from the second order, that just says that, okay, e to the 0x, right, which is just 1, is a solution. E to the negative 2x is a solution. And e to the negative 1x is a solution. All right, so what would be this super linear combination?
Or, I guess it would be C1.
All right. Oh, so the linear combination, we could say, okay, y of x equals
C1.
c1 times y1 plus c2 times y2. Oops, not y squared, y2. C sub 3, y sub 3 is a solution as well for any choice of c1, c2, c3. So y1 is just 1. I get c1 plus c2, y2, and that's e to the negative 2x, plus c3, e to the negative x. And this would be general solution. Okay. So just to see this example, we took it up to a third order. We got 3 linearly independent solutions. And we're going to talk more about what that means when we have 3 or more functions. What does it mean to be linearly independent? Well, if I have a third order equation and I have 3 linearly independent solutions to that homogeneous equation, then this captures all potential solutions. In other words, any solution will be of this form with a particular values of C1, C2, and C3 in there. So no other solution outside of those linear combinations that captures them all. Okay? Next time, well not next time, but on Tuesday, we'll see what happens if we have repeated roots.
We have 4
Oh yeah, we did that once. Right. We're going to do a third order with repeated roots. All right, but we're going to call it quits for today. All right, we're going to talk about the exam. And obviously that's Thursday.
Can you pull it down a little bit?
Yeah. This is like a blanket, yeah, that will not cover my head and my feet simultaneously.
Oh, no.
Turn sideways.
I know. All right. So Thursday the 24th. Tomorrow's Wednesday. Yeah. Okay. So we got our exam, and it's going to cover 1.1 through 2.4 in the book. Now, does that mean there's going to be types of problems from every type of, every section? No. But that's all material in there is fair game. Okay. You're going to have the entire class session. Not going to come in and start talking about second order, third order, or anything like that in here. Okay. So we'll just start with it right away. And here's the thing I came up with now. There's going to be a short, no calculator portion. Okay. Short meaning it's not going to make up half the exam. But, the calculators are pretty sophisticated. They could do all sorts of stuff. I mean, not only integration, differentiation, but you could generate a direction field for a first order equation. you can solve a first order differential equation, it will do it for you. So these are going to be, mostly basic type stuff. I want to know that you can do some of that stuff without the calculator. So stuff on there that is fair game, things like verifying a particular solution or given solution to a differential equation. So I could say, hey, verify that the function blah is a solution to this differential equation. Okay, that's fair game. You may have a problem where you're asked to match first order, TCH, match. Math. You can do math on that part. You can match given differential equations to their correct direction field. Okay. So you got to use some logic, ruling out. This one's autonomous, and so it should have this property. I noticed that dy dx involves a factor of x. So if x is 0, dy dx equals 0. What should that look like? So using logic to rule out the other ones and explaining your choices, things like that. And computing simple first order equations, solving. So things that are separable. I don't think I'll have any linear ones where you got to do the integrating factor if you have to do that by hand. So that probably wouldn't be on the no calculator part. So solving simple first order equations.
So like separable.
Yeah, separable, stuff like that. All right, the second part, the calculator portion, of course. You can use, however, on the whole thing, a sheet of notes.
Game changer.
8.5 by 11, so 1-page notes will be allowed throughout.
By 6 mil.
Split it in half, don't say.
Has anyone ever had Kitiguchi?
Uh,
Requires it be what?
What does he do?
He requires that it's less than 6 mils thick, because somebody brought in a cube.
Oh. Okay, so it's two-dimensional. One page of notes allowed throughout the exam. 8.5 by 11 is fine with me, but both sides. That's fine.
That is awesome.
Okay, and there will be no take-home portion.
Just take us away from getting stuff. Get the answers out by looking at the board.
Yeah, take-home portions, yeah, if it's going to be a take-home, to make it worthy, you generally look for 2 difficult problems as opposed to 5 problems that you could do in 10 minutes in class or something. But yeah, once as an undergrad, I spent, I don't remember how many hours, it was 22 hours over a weekend on a take-home portion of an exam. And I did really well. But I burned myself out. That was week 6 of the term or something like that. I didn't do anything for the last 4 weeks, just burned out. What's that?
What class was it? It took 22 hours. Was it 22 hours of like computation?
That was advanced calculus. That was analysis.
Oh man, that's crazy.
Yeah, it's not fun.
That on.
All right, so that's what we got.
Wait, what's the calculator portion?
Calculator portion could be any of that, but
But harder.
well, also linear. No, so.
Oh, no.
Make sure.
Population probabilities.
I'm not going to list out. See, here's the problem with making a list. If you don't see something in the list, does that mean it's not going to be in there, or is this just a list of things you will see?
Well, you already said 1.1 to 2.1.
Just
1.1,
Yeah, that's pretty fair.
2.4, but you could have, you will definitely have linear first order. In that case, what's the method of attack?
Integrating factor.
Yeah, integrating factor. Yeah, find that rho of x, multiply both sides by it, and then that makes the left side recognizable as, well, it's the derivative of this product, and then you integrate both sides, try and solve for y if it's reasonable. So linear first order, you could have Bernoulli. It's fair game, but I'm not saying it's going to be on there or not.
Substitution.
Homogeneous, first order homogeneous. Now, I don't like the fact that that word homogeneous means different things, you know, with the first order as it does with the second order, but first order homogeneous, I like when it just means the right side equals 0, but this is of the form dy dx equals, and the right can be massaged in some way, so it's a function of y over x. Anytime a variable appears, it's only in the form y over x, so you can make a substitution. And follow that. I prefer to just call it, it's just a variable substitution. You're just doing a change of variables instead of y over x. If y and x only occur as y over x, call that another variable. And you might be able to rearrange that so that it's first order, linear in V, or separable. And then you put separable.
Separable usually comes with one of those, right?
Well, Bernoulli wouldn't necessarily be separable.
No, I mean, like, after you've done your, like, in your integrating factor, you would eventually get separable usually.
You just get integrable on one side. You integrate it, and then on the left-hand side, you got some function times y. And you divide out, solve.
Or the homogeneous too.
Speaking to the fact of the air resistance problem.
I would have the formula for velocity and position, assuming linear, so proportional to velocity only, not proportional to square velocity, nothing like that will be on there. Probably no Newton's law of gravitation problems like escape velocity, things like that. That was sort of like, oh, these are other things they talk about, it's cool, worth your time to look at.
Like air
I'm not going to put that on there, but could be an air resistance problem.
But we wouldn't need to write that giant equation down, or you would provide for it, you're saying?
Yeah, I might do that. That's a good idea.
Yeah,
So
I
that
think
would
I
want
want to
to
space.
derive
Might
that,
as well
right?
write it
That's
down.
okay.
Derive.
Essentially,
Yeah, I was curious. Yeah, might allow, but if you can give it to us, then I won't write it down, I won't wait.
Air resistance proportional to velocity. If that's the case, I will provide the equations. I certainly don't, you know, it's displacing some room for other stuff.
What's maximum displacement?
Can we put a table?
Take the mixer.
Yes, yes.